Hi, my name is Alyssa Murphy, and this is Lab 3 for Physics 2211. So going over a brief introduction, first the purpose of this lab was to use principles of gravitational force and circular motion to determine the mass of a black hole and the speed at which a spaceship must go in order to escape the black hole. The concepts we review are Newton's second law, circular motion, gravitational force, and then position and velocity update. So the equations that will be used, over here we see that F net equals dp over dt, and then momentum itself is mass times velocity, and then we'll be using this dp dt and F net correlation to solve for curving motion. So we see that dp dt equals dp dt parallel plus dp dt perpendicular, which then we can use again to say that the F net equals F parallel plus F perpendicular. And then we'll be using this equation to solve for the parallel component of the change in momentum, which will be the change in the magnitude of the momentum times the direction. And then for gravitational force, this is the typical equation that we use. And then the update formulas, again, are the same. RF equals RI plus V average delta T, and VF equals VI plus F net over M delta T. So in a brief preview of the results, here we calculated F net parallel, and F net perpendicular, and then the mass of the black hole was found to be 9.8 times 10 to the 33 kilograms. And then in part 2, we found that initial ship speed should be negative 4.2 times 10 to the 7th, 1.9 times 10 to the 6th, and then 0 meters per second. And then we see the planet's orbital speed here in the orbital period. And then at the end, we found that the ship was about 3.1 times 10 to the 11th meters away from the black hole. So for the first computational model, going over some initial conditions, this system for this part is considered the star, and the surroundings is the black hole. So I inputted my Georgia Tech email, and then the mass of the star, which was 2 times 10 to the 30th kilograms, and then the time interval, which was supposed to be set to 1 day in seconds. So then going into the calculation loop, P initial and P final are calculated using P equals mv for each one, and then delta P and delta V were calculated using the V final minus V initial and P final minus P initial, and then dp dt was calculated with delta P divided by delta T, and then we could say that because of Newton's second law that F net equals dp dt, and then using that equation we talked about earlier, we can calculate the parallel component of dp dt with P hat and the magnitude of the change in the magnitude of momentum. And then we can, again, use that second law to say that the parallel and the perpendicular components equal the total net force. And then down at the bottom, we rearranged the gravitational force equation to solve for the mass of the black hole. So in the results, this is the video of the results, and then the mass changes based on the intensity of the gravitational force, and the gravitational force is different based on the distance from the black hole. So then the mass to overall was found by averaging all the values, which was calculated to be about 9.8 times 10 to the 33 kilograms. So then for the second computational model, the initial conditions, the black hole initial mass was set to be what we calculated in part 1, and then the time I set to be the 1 period of the planet, and then these were those initial ship speeds that we talked about earlier that were found based on guess and check. The system for this lab is the spaceship, and then the surroundings is the planet and the black hole. So going into the calculation loop, the force of the black hole on the planet was calculated using the gravitational force equation, same for the force of the ship on the planet, and then the net force on the planet was a combination of the both, and then the same exact thing is the case for the net force on the ship. And then down here, planet and ship velocities were calculated using the velocity update formula, and then the positions were found using the position update formula. So here's the results. Again, that's that initial that initial velocity that we calculated using guess and check, and then here were those orbital speeds, that orbital period, and then how far away the ship was. So going to error. In part 2 of the lab, it's possible that the velocities found were not the minimum possible velocities because they were calculated just using guess and check approximations. And then the final distance of the ship from the black hole could be too small, as the period of the planet was rounded when I inputted it to be the time for running the simulation. So for the what does it mean question, we're asked to discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum. So I said that F net and its components are the same thing mathematically as dp dt and its components. However, in this case, F net can't be calculated directly because we don't have the mass of the black hole, whereas dp dt can be calculated using the velocities and the mass of the star. So in the what if question, we're asked to find initial velocities of a spaceship where the spaceship would enter some kind of orbit around the black hole. Again, through just guess and checking lots of different velocities, I found that one possible option would be negative 9 times 10 to the 4th, 1 times 10 to the 7th, 0 meters per second, which gives us this kind of elliptical orbit seen by the spaceship with the magenta color. Thank you very much.